Let us talk about limits of sequences. So, firstly, what is a sequence? So, we will be talking about sequences of real numbers. We have already seen integer sequences earlier in this course. Well, a sequence of real numbers is much like an integer sequence, except instead of integers you have real numbers. So, a sequence of real numbers we will write it like this, a n in curly brackets, and what this necessarily usually means is that n runs over natural numbers, is a collection indexed by integers, by natural numbers. So, there is a1, a2, a3 and so on. So, for every natural number you have a real number. If you want, you can just think of it as a function from natural numbers to real numbers. Okay. Let me just give you some examples that you should keep in mind going forward. So, let us just look at the sequence a n is equal to n. So, this is actually a sequence of integers. The second example I would like you to keep in mind is from my lecture on least upper bounds. A n is 1 minus 1 over 2 power n, related to my sad story of trying to run a marathon. And the third sequence I would like to keep in mind is a n is equal to minus 1 to the power n. So, what is this last sequence really? So, a1 is minus 1 to the power 1. So, let me just write it down, write down the first few terms. So, the first term is minus 1, a2 is minus 1 into minus 1, which is plus 1, a3 is minus 1 into minus 1 minus 1, which is minus 1. So, it just alternates plus 1, minus 1, plus 1, minus 1 and so on. Okay. So, some basic definitions. So, firstly I will say that a sequence is bounded above if well the set. So, if you have a sequence you can look at the underlying set, the set a n belongs to n is bounded above. This was a definition that we talked about last time, but it is really much simpler in the case of sequences. All we are saying is that there exists a real number a, which we will think of as the bound, such that every term of the sequence is less than or equal to a. For every natural number n, a n is less than or equal to a. Let us go back to our examples. So, this sequence a n equals n, this is not bounded above, and the fact that it is not bounded above is precisely the Archimedean property of the real numbers. The second sequence a n equals 1 minus 1 over 2 to the power n. This is obviously bounded above. 1 is an upper bound for every term of the sequence. Every term of the sequence is less than or equal to 1, in fact is less than 1. This third sequence, which keeps oscillating between plus 1 and minus 1, this is also bounded above. It is bounded above by 1. Every term of the sequence is less than or equal to 1. So, 2 and 3 are bounded above, example 2 and example 3, example 1 is not. Alright. And another definition is that of a weakly increasing sequence. So, sometimes it is called a non-decreasing sequence. A sequence a n is weakly increasing, and you will find in many textbooks non-decreasing. This seems too much negativity in this non-decreasing. So, I prefer weakly increasing. If a n is less than or equal to a n plus 1 for every n in n. So, each term of the sequence is at least as large as the previous term. Okay, if I just said increasing, it sometimes refers to the fact that each term is strictly greater than the previous term, but here we will just be using weakly increasing. So, let us go back to our examples and look at these sequences. The first sequence is certainly weakly increasing, in fact, it is strictly increasing. The second sequence is also weakly increasing. We had drawn these points on the interval. We had seen that we start with half, and then we go to 3/4, and then we go to 7/8, and then we go to 15/16, and they keep increasing towards 1. This third sequence, it oscillates, it is not weakly increasing. A3, A1, A2, A3 is certainly not greater than or equal to, or maybe I wrote it like this is certainly not true for the third example. So, the first two sequences are weakly increasing, whereas the third is not. Okay, so suppose you have a sequence that is bounded above and weakly increasing. Then what can you say about the set S? If a n is bounded above and weakly increasing. Well, the set S, it is bounded above, and let A be the supremum of S. What we have seen while studying the least upper bound of a set is that for every epsilon greater than 0, there exists x in S such that x is greater than a minus epsilon. Now, what is the set S? The set S is just the values of the sequence. This can be rewritten as for every epsilon greater than 0, there exists a natural number, let us call it capital N in N, such that a n is greater than a minus epsilon. Now, remember this sequence a n is weakly increasing. So, I have a n which is greater than a minus epsilon, but a n is less than or equal to a n plus 1, which is less than or equal to a n plus 2, and so on. So, what I get is for every little n greater than capital N, a n is greater than a minus epsilon. Notice also that since a is an upper bound, I can write this as a is greater than a n is greater than a is greater than or equal to a n is greater than a minus epsilon. So, what we get is that for every epsilon greater than 0, the values of the sequence after n are within a distance of epsilon from a. The values of the sequence a n become really close to the supremum a. So, this is a special case of what is called the limit. If we go back to this example 1 minus 2 to the 1 minus 1 over 2 to the power n, which we studied in some detail, this sequence a n, its values get closer and closer to 1. They never quite get there, but they get within epsilon of 1 for every epsilon positive. So, this motivates the definition of the limit of a sequence. This is a very important definition, and if you understand this definition, then you have understood the core of mathematical analysis, which includes sequences, series, derivatives, integrals, and all of that. So, let us try to understand this really well. So, we say that a sequence has limit a. So, sequence a n has limit a, which we write as limit n tends to infinity a n is equal to a if for every epsilon greater than 0 there exists a natural number n such that for all little n greater than capital N, a n is really close to a. So, what we would say is that the difference between a n and a in absolute value is less than epsilon. Okay, this last bit here I can rewrite this as a n lies between a plus epsilon and a minus epsilon. If you think of this, the points of the sequence on the number line, you have this limit a and you take any epsilon positive, a plus epsilon is going to be a point slightly to the right of a minus epsilon is going to be a point slightly to the left of a. And what you are saying is no matter how small this epsilon be, as long as it is positive, the terms of your sequence, which maybe this is a1, this is a2, maybe this is a3, this is a4, this is a5, you exclude finitely many terms, all the remaining are going to lie inside this interval from a minus epsilon to a plus epsilon. The sequence a n is said to be convergent if it has a limit. If we want to say that a sequence has a limit without actually specifying the limit, we would say that a sequence is convergent. We will see an example of this kind of usage later. So, let us look at our favorite example at this point. So, we have this sequence a n is equal to 1 minus 1 over 2 to the power n, and I claim that limit n tends to infinity a n is equal to 1. So, how do we know for sure that this is the case? So, following the definition, we need to say that for any epsilon greater than 0. So, we would say let epsilon greater than 0 be given. So, given any epsilon greater than 0, I need to convince you that there is a natural number capital N. Let us do some rough work over here. So, I want a natural number capital N such that if little n is greater than capital N, then a n lies between 1 plus epsilon and 1 minus epsilon. So, 1 minus epsilon is less than a n is less than 1 plus, well, a little n is less than 1 plus epsilon. Now, a n is 1 minus 1 over 2 to the power n. I want to show that this lies between 1 plus epsilon and 1 minus epsilon. This second inequality over here is not a problem because 1 plus epsilon is larger than 1 and 1 minus 2 to the power n is less than 1. So, certainly 1 minus 2 to the power n is strictly less than 1 plus epsilon. I need to worry about the inequality on the left. Well, this is the same as saying that epsilon is greater than 1 over 2 to the power n, which is the same as saying that 2 to the power n is greater than 1 over epsilon. But I can make sure that I know that 2 to the power n is already greater than n. We proved this by induction, remember? And so that, and then using the Archimedean property of real numbers, well, this 1 epsilon is really small, 1 over epsilon might be something quite large. But we know that given any real number, there is always a natural number that is bigger than it. So, now we have done our rough calculation, we are ready to write the proof. So, let n belong to n be a natural number such that n is greater than 1 over epsilon. Then absolute value of 1 minus I guess I want to say a n minus 1. Well, this is equal to just absolute value of 1 over 2 to the power n. Well, 1 over 2 to the power n is positive. So, this is just 1 over 2 to the power n. Well, 2 to the power n we know is greater than n. So, this is less than 1 over n, but little n is greater than n. So, if little n is greater than capital N, this will be less than 1 over n, which is less than epsilon. So, this is true for all n greater than little n greater than capital N. So, that is the proof that this sequence converges to 1. Here is another example, and I will let you try this yourself. Limit as n tends to infinity 1 over 2 to the power n is 0. Okay, and here is another thing you can think about. What if, so I am taking powers of half and they seem to become, okay, so half, 1/4, 1/8, 1/16, they become small pretty fast. What if I were to take limit as n tends to infinity of something less than 1, but pretty close to 1. So, let us say I took 0.99999, that is very close to 1, and raised it to the power n. Would that still go to 0? And what if I took something larger than 1? Then what would happen? So, now I will tell you some general methods for trying to firstly figure out if a sequence is convergent or not, and secondly to try to find the limit of a sequence. So, you do not always have to these proofs with epsilon and n, they help us to establish the limits of some basic sequences, but in practice once we have a catalog of some basic sequences whose limits we know, we do not keep using these arguments with epsilon and capital N. We use other tricks to find out what the limits are. So, the first basic thing is about the existence of the limit, the convergence. This is more or less a direct consequence of the completeness axiom for real numbers. If a n is a weakly increasing sequence that is also bounded above, then a n is convergent. I will not go and write down the proof of this, because this is where we actually when we wrote down the definition of a limit, we actually started with this example, but I will just tell you how the proof would work. The limit of the sequence will be just the supremum of the set a n n in n. Okay, and now if you use the characterization of the supremum in terms of epsilon, you will see that this is exactly the statement that limit of a n as n tends to infinity is equal to the supremum. What if the sequence is not weakly increasing, but say weakly decreasing? Okay, so this kind of thing is not very difficult to deal with. So, if you have a sequence a n, you can talk about a sequence negative a n. So, if the sequence a n has limit a, then the sequence negative a n will have limit minus a. So, if you have a weakly decreasing sequence that is bounded below, then that will also be convergent. We put together these notions of weakly increasing and weakly decreasing under one name. We call them monotone sequences. It is either weakly increasing or weakly decreasing. Okay, and we say that a sequence is bounded if it is bounded above and bounded below. So, another way of writing it is that there exists a real number which we will call the bound m in R, such that every term of the sequence lies between plus m and minus m. So, such that a n is less than m for all n in n. Every term of the sequence lies between a fixed upper and lower bound. And combining our statements about weakly increasing sequences that are bounded above, weakly decreasing sequences that are bounded below, we can say that every bounded monotone sequence is convergent. How do we know that the limit of a sequence is unique? So, what I will say is that suppose we have a sequence can it converge to two different numbers? So, let us say it converges to A and it converges to some other number, let us call it B. Then I claim that A is equal to B. To prove that A is equal to B, it is enough to show that for every epsilon greater than 0, the absolute value of A minus B is less than epsilon, as we have seen in an earlier lecture. So, let us do that. So, in order to do this, so let us say we are given epsilon greater than 0. Then firstly, I can choose n1 in n such that for all n greater than n, a n minus a is less than epsilon. Well, but I can also take epsilon by 2, because if epsilon is positive, then so is epsilon by 2. So, there exists n1 in n such that a n minus a is less than epsilon by 2 for all n greater than n1. And similarly, since the limit of a n is b, I can choose n2 belongs to n such that for all n greater than n2, a n minus b is less than epsilon by 2. Now, using these two statements, we can bound the distance between a and b. So, let n be, take the larger of n1 and n2. So, I will call that max of n1 and n2. Now, that is greater than or equal to n1 and greater than or equal to n2. Let us add 1. So, then what we have is n is greater than n1 and n is certainly greater than n2. So, for this value of little n, both these inequalities here hold, and using that we can conclude that a absolute value of a minus b, well, that is I can write that as a minus a n plus a n minus b, and using the triangle inequality this is less than or equal to a n minus a, well, that is the same as a minus a n plus a n minus b. Now, a n minus a is less than epsilon by 2 and a n minus b in absolute value is less than epsilon by 2. So, this whole thing is less than epsilon. So, what we have shown is that the distance between a and b is less than epsilon for every positive real number epsilon, and so a is equal to b. So, we conclude that a sequence can only have one limit. Now, I will come to some basic properties of limits. The first, so these are arithmetic properties of limits. If limit as n tends to infinity of a n is a and limit as n tends to infinity of b n is b, then we can look at the sequence whose nth term is a n plus b n. Is a plus b. The second property is that if limit as n tends to infinity a n is a and limit as n tends to infinity of b n is b, then you can multiply the terms, you can get the sequence whose nth term is a n times b n. This is a b. The third property is that if the limit as n tends to infinity of a n is a and a is not equal to 0, then you can look at the sequence which takes values 1 over a n. So, then limit as n tends to infinity 1 over a n is equal to 1 over a. There could be a slight issue with this 1 over a n. It could be that some terms of the sequence are equal to 0 even though the limit is not 0. In that case we just ignore those terms. You will see that with sequences ignoring a finite number of terms does not really make any difference as far as limits are concerned. And the fourth and final property is that this is not quite arithmetic, it is with inequalities, and this is going to be really useful as you will see. If a n is less than or equal to b n for all n in n, then the limit okay, yeah. If limit of a n is equal to a and limit of b n is equal to b, and each term of a n is less than or equal to the corresponding term of b n, a n is less than or equal to b n for every n in n, then a has to be less than or equal to b. Now, using these rules we will be able to compute a lot of limits using some basic limits that we have computed.